Good evening, everyone, and thank you for joining us. It's my very great pleasure to welcome you all to this year's Marsden Lecture, in which we will be continuing an annual tradition of celebrating ideas that can shape the future of healthcare. Our founder, William Marsden, believed that care should be based on need rather than wealth. And nearly 2 centuries later, that principle remains central to the NHS. But the landscape in which we deliver that care has changed beyond recognition. As you will probably know, the NHS is under unprecedented pressure. Demand is rising, our systems are complex, the burden of chronic disease is growing, and expectations of what medicine can achieve are higher than ever. And at the same time, advances in data science, engineering, genomics, and all sorts of other medical technology are really advancing at a pace that's difficult for large systems to match. We know that if the NHS is to remain sustainable, innovation can't sit on the margins. It must be central to how we diagnose, treat, and support patients, and how we organise and deliver care. And here at the Royal Free London, we're absolutely determined to play a leading role in that future. Our partnership with UCL gives us access to world-class research. Our clinical teams are hugely ambitious and highly committed to improvement, and our hospitals serve diverse communities whose needs demand new approaches. We've seen firsthand at Royal Free London how innovation can do all sorts of things that really bring benefits to patients and change their lives, from shortening pathways to transforming outcomes. And that said, we've also been immensely frustrated by some of the barriers that have been in our way when we've tried to do those things. And that's really why our partnership with the Royal Free Charity is so important to us. The Royal Free Charity really helps us to allow innovation to take root and to grow, and to allow us to explore what's possible rather than just what's affordable. In just a moment, you'll hear from the charity's chair, Judy, Dewinter, who will introduce our guest speaker. But before I hand over, I'd like to extend a special welcome to some of our former Royal Free London colleagues who are with us this evening. Professor Sir Stephen Powis, who has recently stepped down as NHS England's National Medical Director, Dame Caroline Clark, Regional Director for NHS London, and Dr. Chris Strether, Medical Director for NHS London. It's lovely to see you all here, and thank you very much for your continued support to Royal Free London. I'd also like to say a huge thank you to the Royal Free Charity for hosting this event. And it's now my absolute pleasure to introduce Judy Dewinter, Chair of the Royal Free Charity.
Good evening, everyone. As Gillian said, I'm Judy Dewinter, Chair of the Royal Free Charity, and it's my pleasure to welcome you all here this evening. Throughout the history of the Royal Free Hospital, innovation and philanthropy have always gone hand in hand. The hospital itself, as you heard, was founded through a visionary act of philanthropy and a belief that medicine could and should be better. That spirit to challenge limitations and to act with purpose has defined the Royal Free in its many iterations for nearly 2 centuries. Time and again, philanthropy has enabled innovation that could not have happened through public funding alone. New ideas, new technologies, new models of care. Today, the Royal Free London has the people, the partnerships, and the ambition to lead in health innovation. What philanthropy provides is the freedom to move at pace, to take bold steps, and to turn promising ideas into clinical reality. Our supporters share this belief, and I want to thank those here this evening for helping us invest in the work that benefits patients across our hospitals and beyond. The same spirit that drove William Marsden to reimagine what healthcare could be is alive in our speaker this evening. Professor Rebecca Shipley has brought together engineering, clinical insight, and cross-sector collaboration to solve some of healthcare's most complex challenges. Her leadership during the pandemic, particularly her work developing breathing devices for COVID patients, is a powerful example of what can be achieved when disciplines combine around a shared purpose. Like Marsden, she's driven by the conviction that care must continually evolve to meet the needs of the time. It's my great honour to introduce our speaker, Professor Rebecca Shipley. She's Professor of Healthcare Engineering and Director of the UCL Institute of Healthcare Engineering. In addition, she serves as co-director of the Chimera Research Hub and as Chief Research Officer at UCL Partners. Please join me in warmly welcoming her to deliver this year's Marsden Lecture.
Good evening, everyone. It's such a privilege to be here and to see so many colleagues and friends that I've worked with over so many years in the audience. So thank you so much for coming. Thank you also to Gillian, to John, to Judy for such generous introductions. And the Royal Free Charity team have done an absolutely stellar job of organising a wonderful evening. So many thanks to them. They're very patient, even though I only sent through my slides at the very last minute. So thank you to them. I have to admit, when Judy first invited me to give this talk, I felt quite overwhelmed as to why she would be inviting me to come along today. But I said yes, so it stuck with me now, and I'm just going to tell my story about the work that I do and why. So the first thing to declare is that I'm not a medic. I have no medical training. And in fact, I gave up biology when I think I was around 16 at school, which in retrospect was a rather daft idea. But because of that, I actually knew very little about William Marsden before I was invited to give this event. And it's genuinely been a privilege to learn more about his legacy. That said, I have been an academic at UCL since 2012, and I think I have collaborated with Royal Free scientists and clinicians since that time. And what's really clear to me is that much of what William Marsden stood for still pervades the culture here today. And that's really clear as someone who's come out, from the university and collaborates with the hospital. On a personal note, my sister is a long-term patient at the Marsden Cancer Hospital in London as well. And I think as, Londoners, my family are very aware of the privilege of having access to that kind of level of clinical expertise and excellence in the city. And of course, that's at the Marsden, but across the city as a whole. So what really inspires me about Marsden, I think, is a couple of things. First of all, a commitment to a set of values. So the fact that he believed in healthcare being accessible to everyone. And not only that, but then a commitment to thinking creatively and with such conviction about how you try and solve those kind of problems. And I think that also speaks to the power of philanthropy. And I think that aligns very much with the ethos of this evening. And I'll try and weave some of those kind of principles into my talk, but I found it genuinely inspirational to kind of revisit those kind of principles and to think about why I do what I do. So hopefully this talk is interesting to all of you on that basis as well. So what am I going to talk about today? So I have a very different background, I think, to probably most people in the room and many of the people that I work with. So I trained as a mathematician, moved into engineering, work as a healthcare engineering academic, have moved into healthcare innovation. I work in data for London. In short, I have lots of different hats, but I don't think it really matters because what motivates me is solving problems. So it doesn't really matter what hats you're wearing when. The point is that I personally am motivated by solving problems and trying to solve problems that I care about. And for me, that is in healthcare. So that's the kind of approach that I come at it with. So what I'm going to try and talk you through today is basically my story. So how I went from starting off doing maths. I've never had a plan in my career. I didn't when I started off doing maths, and I certainly don't now. So I'm going to try and talk you through kind of how, as a mathematician, I ended up working in healthcare, why I think that brings a real kind of freshness and of thinking that is really relevant and we could do more of. But then talk about how that led to healthcare innovation work in the pandemic and what I'm trying to do now. So this is where I started off my academic career. This is the Mathematical Institute in Oxford, which is a concrete building that's almost as beautiful as the one that we're in here. And I did my undergraduate degree there, so I trained as a mathematician and then did a DPhil or PhD there in the Oxford Centre for Industrial and Applied Maths. And I had no idea really how lucky I was to be there, but The centre was full of people who had a similar background to me, so they trained in maths and computing, but everyone was trying to tackle real-world problems. And, for me and everyone else that I worked with, maths is really a language to try and understand the world around you. So it's a way of describing physics, biology, chemistry, and how those interact, and to give us a better fundamental understanding of how systems work and how the world around us works. And people worked on all sorts of different problems, and I've put a few fun ones up here just to kind of give you an idea of the breadth and how kind of daft some of them might seem. But I remember people doing PhDs at the same time as me who were working on things like how you coat donuts with films of sugar, how you use maths to understand the different balance of mechanics and different chemical cues that mean that you can predict how shells form the shapes that they do, how jellyfish swim. So jellyfish are thin sheets of material that swim within a kind of pervading current, and I'll come back to that in a moment, through to kind of radar systems. And of course, I moved into biology, which I'll tell you about in a moment. But what's key in all of these is that, as I said, maths is used as a tool to kind of understand how the system works, so to understand the physics, to understand the chemistry, to understand the biology. And it gives a kind of integrator that allows you to then better understand what's happening, but also use that as a predictive tool that you can then optimize, and that obviously feeds into technologies and engineering and manufacturing and all sorts of different fields. So I basically grew up in an incredibly rich environment of people who were interested in solving problems, in learning lots of different things, and exposed to all sorts of different application areas. And I honestly didn't know I was born. I didn't know that that wasn't necessarily normal. And to give some of the examples, this is a lovely video of jellyfish swimming. And as I said, jellyfish is essentially, it's a thin elastic sheet that moves in a current. And if you can develop a fundamental understanding of these kind of behaviours and mechanics, then that translates into all sorts of different fields and arenas. For example, heart valves have a similar set of properties. So you can see how, even though you work on these kind of very kind of simple, complex, maybe abstracted problems, there's opportunities to translate them into different sectors. Another one is coating donuts with films of sugar. So here you can see, and I remember it was my colleague who was called Ian Griffiths who spent about 2 years modelling this process. And basically this involves a liquid sheet of sugar, which is quite viscous, falling across a donut that moves through it. And of course, that sounds like quite a niche problem to try and solve, but we all eat Krispy Kreme donuts, so there is a wide market for it. But it's also very translatable to other fields. So if you think about other coating technologies that pervade our everyday lives, whether that's how you spray cars with paint or circuit board technologies. And this was the kind of environment that I kind of grew up in academically, if you like. But quite quickly, I got very interested in mathematics and biology. And I says it's quite interesting because I gave up biology when I was at school, because at the time, apologies to those in the audience who didn't, but I didn't find it that interesting. I found it as if you were kind of being taught to rote learn different aspects of biology. Whereas suddenly I got exposed to using maths as a tool to try and understand biology. And that involved doing things like understanding the balance of fluid mechanics when blood flows, or when cells move around in a tissue, what the balance of forces are that they're doing that under. And then using that as a tool to better understand kind of biology, and in turn, obviously, that has implications on healthcare. So this is a neat video of the idea being that these are red blood cells that are moving in a pervading flow, and hopefully everyone can grasp that the fluid mechanics of that are quite interesting. So I basically latched onto this because I found it really interesting. So again, there's been nothing that I've ever done which has had more of a plan than that. So I literally did this because the maths was beautiful, and I found it very interesting. I still feel that to this day. So the work that I do now still has very strong components of this, the research that I do at UCL. So this is, yes, my obsession with blood vessels. So why are really small blood vessels really important? So I don't know how many experts in physiology or not we have in the audience, but obviously when you breathe in oxygen. That oxygen gets transmitted into your bloodstream, and that gets circulated around your body through your blood vessel networks. That gets exchanged into your tissue at a really fine scale. So you have a network of really small blood vessels called capillaries, which are very small, like fractions of a human hair in terms of the diameter. And that's where you have this combination of a fluid flow with cells in it, so blood cells like you have here, and they carry oxygen, and that oxygen what you call diffuses out into the main tissue. Of course, if you deliver a drug to someone through the bloodstream, so for example through an IV drip or something, that will get delivered through the same blood vessel network. So it's incredibly rich from the point of view of maths, because it gives rise to all sorts of interesting problems around the fluid mechanics of how you get cells suspended in a fluid and how that flows under different pressure gradients. But it's also really important because it determines all of the transport properties of how, for given structures, you then get things like drugs and oxygen, etc., out into a tissue. So there's a lot of fundamental problems that are really interesting in terms of understanding how the body works, but there's also lots of therapeutic avenues that it's really relevant to. But as I said, I got into it just because the maths was lovely. That's kind of thinking of an individual vessel, like right down if you're zoomed into an individual capillary, and that's kind of why they're super important. But of course, these form really rich structures as well, which in their own turn are very beautiful. So these are examples from the heart and a little section of brain on the right-hand side. And there's a few things that I wanted to get across here, which is because every organ in your body functions differently, it will have a different structure of blood vessels to facilitate that function. So what I think is incredible is that if you go around every bit of your body and look at the really small blood vessel architectures, in every bit of the body, they will look very different to facilitate the function of that tissue. And obviously, I think it's very interesting to then understand what that structure means in terms of how the tissue functions and what that means in terms of healthcare and medicine. So there's the structural element of this, which makes this really interesting. But of course, it's very hard to measure what those structures look like because of the kind of imaging tools that requires. So this one on the left is a heart, a little section of heart muscle, basically. And you can see the richness of the architectures. The smallest vessels there are about 10 microns in diameter, which are about a quarter of the diameter of a human hair. And those were measured outside of the body. The one on the right is a very small section of brain tissue. It's about the size of a pinhead, if you like, and that was actually measured in situ in the body. But hopefully you can see at least that the structures are very different, but you can imagine then if you want to do things like understand how drugs get delivered in the brain versus the heart, it's really important to have this level of understanding of what the vascular structures look like and why. And then the other factor is that, again, structures are very different in health and disease. So we all, hopefully, if we're in good health, will have relatively well-structured, organised vessel structures. And this one on the left, this picture on the left, is an example of what that might look like. That's a sheet in your gut, and you get these really nice like basket structures, which are very regular and nice to predict. If you're interested then in thinking about what happens in disease, many diseases have characteristics where they have very disrupted blood vessel structures. And so if we want to understand disease and how it progresses and how we can diagnose it, it's really important to understand what happens to those structures and what that means in terms of what we can measure. So these are some examples of networks from different cancer types, and you can see that they're chaotic by comparison and harder to predict. So not only did I get a bit obsessed with the maths, but I also got a bit obsessed with understanding the correlation between structures and the maths and what we can measure. And when I started out, we couldn't measure many things, and that's a recurring theme that I'll come back to at various points during the talk. I've kind of already mentioned this, but why is this really important for diagnostics and therapies? Well, as I said when I was trying to describe kind of the function of capillaries, they're very important for delivering oxygen, which is very important for healthy function, but also drugs. And if you have an abnormal blood vessel structure like you do in, for example, a cancerous tissue, what you'll get is regions around the blood vessels, which are the main bits where a drug might get to, for example, a chemotherapy drug. This is doxorubicin, which is a kind of mainstay chemotherapy drug. But as you get further away from the vessels, especially when you've got really odd structures, you'll get pockets that the drug doesn't get to. And what's really important is that if we can better understand what the structures look like and measure them, then can we better design dosing strategies, for example, that might be relevant to, for example, new cutting-edge therapies that are becoming available. So this is a very rich problem for an engineer or physical scientist to try and tackle. And the last bit of the puzzle that I got a bit obsessed by, and then I'll stop telling you the background to why I got really into this, is that I mentioned that capillaries are really, really small, and that's kind of where the action happens in terms of delivery and interaction with your tissues. But of course, it's very hard to measure anything at that scale in your body. So capillaries, as I said, are fractions of human hair. So we don't have the imaging capabilities to be able to look at those for individual patients or individual tumours. But what we can do is use diagnostic imaging scans like MRIs, for example, which give you grayscale information on the scale of millimetres to centimetres. And on the right, that's an example for the brain. And what I got really interested in, and still am, is if we know a lot of information about what's happening at the really fine scale, can we better understand what we measure at this scale and use it as a tool to better diagnose disease or disease progression? Now, this is how I started looking at this. So this is a page out of my PhD thesis, and everyone laughs, but I was talking to some friends before this, and actually this is probably the slide that makes me feel most comfortable in this talk, because it's the way that I think, and it's the way that I was trained. And this is a description of blood flow in really small blood vessels and how that multi-scale interaction happens. But what I think, I put it up to be kind of to make the point, but I think what's really important is that if you bring different ways of thinking about a problem together, then that's complementary and it adds a lot of value. And so for me, coming at these problems as a mathematician, I think about them in a very different way. So I look at this and I have an immediate intuition for how a system works. This is what gives me that intuition. And this is how I came into this world, of working in medicine and healthcare. So this is an example from my PhD, which, as I said, was all about modelling blood flow and drug delivery in really small vessels and doing that kind of multi-scale averaging bit. By the end of my PhD, I was in the maths department in Oxford, but what really clicked with me is that I wanted to be able to use maths as a tool to understand what was happening, but I was also really driven by trying to make it useful and have an impact on healthcare ultimately. And that means that you need data and you need clinicians and you need biologists and you need questions, which we didn't have at this stage. And that was partly because the imaging technologies weren't available, but partly because I was sat in a maths department and I wanted to get closer to those kind of scientists and clinicians. And so I moved to UCL in 2012 and I moved into healthcare engineering. And UCL is genuinely, if you're someone who's interested in working with people from a whole range of different disciplines, it's like being a kid in a candy shop. You can pretty much think of any expertise you might want and you can look someone up and find them. And the culture is such that that person will be keen to have a coffee and chat and collaborations flourish. So for me, it's been the most brilliant environment to be in. So when I started this out and moved to UCL, these images on the left were the kind of mainstay of how we could get access to any of this really highly detailed information on vascular architectures and structures. And these were done by a process called corrosion casting, which is now very out of date, where you flow into an organ a material that then solidifies and then you kind of melt away all of the tissue and you image it. And there's lots of reasons why that causes all sorts of artifacts. And, what you get out might not be quite as representative. There's also issues with resolution. That was the kind of cutting edge at the time. Obviously, this was around 2010. But some of the people involved in this work were at UCL, and I did exactly what I just described to you, which was I emailed them and had a coffee, and I'm still working with them to this day. But that was my motivation, was to start bringing the maths closer to reality, to use it as a tool. And so Simon Walker-Samuel was the person that I had a coffee with. We subsequently set up the Centre for Computational Medicine, which is all around doing this kind of work. And we've since developed, through Simon, imaging technologies, which I'll talk about in a moment, and really intimately linked them with the maths and the modelling work to make tools which are hopefully becoming more and increasingly useful in medicine. And I'll talk you through a bit of that. But I did want to give a very strong nod to Richard Ross and the Rose Trees Trust. So back in 2012, when I joined UCL, obviously as a new academic, you're trying to set up your lab, recruit people into it. And at the time, the kind of work that we're doing wasn't standard. I think now you hear a lot more about multidisciplinary research and there's much more flexible funding for bringing disciplines together. At the time, there wasn't much. And Simon and I were both early academics who were writing lots of grants and trying to get money in. And we applied to the Rose Trees Trust Interdisciplinary Prize, which still runs to this day. And there was one prize nationally, and at the time, this was actually in 2016 when we got it, it was for research at the intersection of maths computing and medicine. And this is our grant application on the right-hand side, which I pulled out and realised that, sorry, Richard, we did very little of what we said we would do, but we did do good things. But this was really transformative for us because it gave us, it was £250,000, and it meant that we could recruit postdocs, we could set up our labs, and there was also sufficient flexibility, which, you know, in the research world you need to respond to, you know, how our research program evolved over time. So I can't estimate to you how important and transformative this work was, and such is the nature of Rose Trees Trust and the team that Richard has built, that, you know, I'm still on the Rose Trees Scientific Advisory Board now, so those relationships stay strong, and I think Rose Trees has a commitment to funding people and to nurturing them, and that has made, as I say, a massive difference to myself and Simon and many others at UCL. So what did we do with the money? We didn't do what we said we'd do. We didn't work on pancreatic cancers, but we did develop some really exciting new methodologies. So the first thing, as I said, was that we wanted access to really detailed information on blood vessel structures. And through Simon's leadership, we developed new optical imaging methods, which basically tag endothelial cells which line blood vessels with fluorescent markers, and meant that for whole tumours in animal models, we could then image the whole blood vessel structures for whole tumour samples down to the smallest vessels. And those are, you know, as I said, a fraction of human hair. And this is a video moving through basically one of those tumours, and you can see the richness and the chaos and the beauty of the structures that we got out. So this was, you know, a massive step change in the kind of level of information that we could get about vascular structures. And of course, there's other similar techniques that have been developed around the world as well. But we did this alongside developing the maths tools. So what we were able to do is take those structures and then reflow them. So we've developed the models, which means that we've basically now got a kind of digital twin for cancer. So we simulate how blood flows through all of those beautiful architectures and how drugs and et cetera get delivered to the outside tissue. And what it means now is that we can now, for example, simulate new drugs where they get delivered. We can look at different dosing strategies, and we can optimize all of this in animal models for now, as I said, but we're hoping to progress, we're progressing to human cell lines. And then this has been a huge program of work for me, and it is to this day, so it's still a very active area of research for me. And I think it nods to expertise here at the Royal Free. We've worked with many of the Royal Free scientists and clinical scientists around this. So actually Brian Davidson just got a new grant last week that was linked to this, and we're collaborators on. We've also worked with many of the people in cell and tissue engineering here, which has been fantastic. But I think the other part of this is that when you come at this from the kind of maths, physical science point of view, you develop frameworks and platforms which can then be applied in all sorts of areas of health and disease. So, as I said, if you're at UCL, it's a bit like being a kid in a candy shop, but we've got excited about then applying these kind of technologies in different areas. And I wanted to just give a few examples of those because hopefully it highlights the kind of richness of the opportunity of working in these kind of areas in these kind of ways. So we're working with Moorfields Eye Hospital around understanding the retina. So the retina, again, changes in the architecture of blood vessels in the retina are indicative of onset of disease, but also there's links between that and other kinds of pathologies in the body. So we're developing tools to do similar kind of work to link structure and function in the eye. We've had a big programme grant through the Engineering and Physical Sciences Research Council, which has been around understanding how breast cancer metastases in the spine go and communicate stress to the vertebra, so we can develop more nuanced predictors of fracture risk. And this is work with multiple different universities, but all builds and clinical sites, and actually does include the Royal Free because we're using explants from here. In the engineered tissue models. But this all builds on the kind of platforms that we developed through this long-term funding. I moved into placentas. So again, as placentas grow, when things go wrong, a lot of that is linked or can be linked to changes in blood vessel structures as they evolve. And so we're developing the similar kind of platforms where we can understand the link between changes in placenta and vascular structures and disease progression, particular fetal growth restriction. And then finally, I've also moved into using the kind of principles around understanding physiology to understand what happens to intensive care patients. And this has been work which was a bit of a shift in expertise, but this is work with UCLH and Great Ormond Street, and uses all of the vital signs monitoring data that gets stored for intensive care patients. And this was funded by the Engineering and Physical Sciences Research Council again, but also the Rose Trees Trust. And what was really interesting about this is that when you look at the models of human physiology that are used as the kind of standard, they're all based on experiments that were done on rats and pigs in like the early 1900s. And yet, because of the partnerships that we have with our trusts, we sit on this wealth of data that is currently not used to inform clinical decision-making and also can be used to inform our models of human physiology. And that's what this grant has been doing. So that kind of closes out me talking about my research background, and I'm going to talk about some more health innovation work from the pandemic. But what I really wanted to highlight was how amazing it is to sit in the kind of ecosystem that we do with world-leading scientists, engineers, computer scientists, mathematicians, but world-leading clinical sites. And as I said, it can yield a huge amount of research and impact, and hopefully that continues to flourish. And then the final thing to mention, and this will lead into the next section of the talk, but so I've talked about the maths, and I've talked about the biology and the imaging. One of the things that we always got stuck on was that we still can't measure things like blood pressures and flows at really fine scales in the body. And so to try and combat that, we started setting up physical rigs where we could try and measure these things. And that's quite hard to do. And, when I said to you that I look at the math slide and that makes complete sense to me, this is the bit that I cannot do. It doesn't make sense to me. But the beauty, again, of being in an academic environment is that you have collaborators around you who can. And so pre-pandemic, I started working with Tim Baker, who's actually here today, around doing exactly this. And what we wanted to do was to set up physical rigs, and I've got an example that I'll pass around here, of the kind of blood vessel structures that I've said that we're imaging, so that we can then we can measure things like pressures and flows and use that to inform our models and to validate them. It's really hard to do things like 3D print vessels that are fractions of, numbers of microns small. So what we ended up doing is having to scale things up and use different methods. And there's a cotton candy machine here, because one of the things that we did was order a candy floss machine off Amazon and use sugar as a kind of sacrificial element, basically. So we built these structures, candy floss, embedded them in a substrate, and then dissolved out the sugar. And then that gives you a network that you can then flow through and measure things. It was fraught with challenge, and we never nailed it totally. But it did serve the template for some of the work that I'm going to talk about next. And this is a 3D printed, scaled up tumour that in reality was about half a centimetre big, but it gives you a feel for it. So thank you, John. So that's the kind of rich academic, multidisciplinary environment that I've come from. And next I wanted to talk about some work that we did during the pandemic, which was much more focused on then delivery of innovation into the healthcare system, but really built off this basis of academic partnerships that I've already talked about. So a bit of a shift here, and apologies to take you back a bit. I'm going to tell the story of what we did in the pandemic because it's really framed my work now in terms of what I want to achieve and why. And of course, many of you in the room were here at the time and of course working here at the Royal Free, so will remember this equally as well, if not better than I did. But if we went back to March 2020, obviously first wave of COVID was starting to hit the UK. And the critical factor really was that we were vulnerable because we had a low number of critical care beds per capita compared to other countries, higher income countries in particular. But also we're not a medical manufacturer of many of our medical devices, we import them. So if you think of ventilators, non-invasive ventilators, pretty much everything on the NHS supply chain, we import them into the country, which of course, when export restrictions were put in place internationally meant that we were vulnerable. So we knew we had an onslaught of patients coming through, but we didn't have enough ventilators or other associated respiratory support kit to be able to match the numbers that were predicted to be coming through. So we were vulnerable as a country. And at the time, the government put out a call, which was the ventilator challenge, to corral our manufacturing and engineering base to help. And the focus there was on mechanical ventilators, which are what you need to support people, for example, in intensive care units who are the most sick when it comes to respiratory illness. And of course, many patients ended up on mechanical ventilators, but we didn't have enough of them in the country at the time. But this really speaks, I think, to another philosophy I want to get across, if you like, that we have a lot to learn from other sectors. So So in the UK, we have a brilliant higher education research base, and we have clinical excellence, but we also have amazing engineering and manufacturing expertise. And I think there's huge value in bringing that kind of expertise into tackling healthcare challenges. That said, we didn't join the ventilator challenge. And again, nothing that I've done has ever had a plan. But I already worked with Mervyn Singer, who's a professor of intensive care medicine at UCL, through that grant that I talked about in terms of modelling physiology in intensive care patients. And Merv is well known for knowing everyone in the world and talking to them all the time. So he was talking to colleagues in China and Italy who had been hit earlier than us with the first wave of COVID. And what they were saying was obviously that they needed mechanical ventilators, but also if they treated patients with non-invasive ventilators or CPAP devices, which I'll come back to in a moment, that could act as a bridge to limit the number of people who progressed to needing mechanical ventilation, but also it helped preserve hospital supplies in terms of oxygen and resources, but also in terms of staff. So if you mechanically ventilate a patient, they're sedated and are usually sedated for a long period of time and would normally have one-to-one nurse provision. And of course, even if we could make tens of thousands of ventilators, we couldn't find tens of thousands of intensive care nurses to support those patients. So if we could keep people off ventilators and preserve our ventilator capacity for the patients that needed them the most, that would be very valuable. And so I went, Tim, I will talk about again in a second, went for a drink with Merv one evening, and he basically said, I think it would be valuable if we could try and make these non-invasive ventilators as well. But I've already spoken about the kind of academic hospital partnerships that we have in place. The clinical academic collaborations were there, so Merv and I already knew each other. But within engineering, as I already mentioned, Tim Baker was one of my colleague professors in engineering, a professor of mechanical engineering design, that had also worked in the motorsports industry for most of his career before coming back to UCL. So we kind of quickly knew that we kind of had the healthcare expertise, we had the engineering expertise, but if we were going to make new devices, we would need someone to make them. And the motorsports industry are very good at gas flow systems and making things quickly to extremely high standards. So Tim reached out to colleagues in the Mercedes Formula One teams. The Grand Prix had been stood down and they had a factory that was not being used, and they dedicated all of their resource to becoming the manufacturers for this work. So here over on the right, you can see Mervyn. David Lomas used to be on the board here, so many of you may remember him. He was my boss's boss at UCL at the time, but he was amazing as part of this team. And then on the bottom here, you can see myself, and that's Tim on the right-hand side, Dave Brearley, who was a critical care anaesthetist at UCLH. Ben Hodgkinson was one of the engineers from Mercedes at the time, and on the left, Andy Cowell was the MD of Mercedes high-performance powertrains. So we managed to form a team with the right expertise very quickly because of existing networks, but again, without a plan. And, you know, because we didn't have a plan and it wasn't strategic, we came together and we had a drink, as I said, and we knew that if we were going to be able to do anything useful, we had weeks, because the peak of the first wave was due to hit by the Easter weekends, and this was mid-March. And so starting by designing a whole new medical device from scratch and trying to get it approved by the regulator wasn't a tractable solution. But I think it was Merv's idea from memory. There was a previously CE marked device called the Philips Respironics WhisperFlow, which you can see a picture of here. That's a very simple device. It's purely mechanical. I've got a replica here, which I'll show you in a second. It's purely mechanical. There's no embedded electronics, which meant there would be a hope of trying to make it quickly. It had been previously CE marked, so it had previously met standards in terms of safety and efficacy. And what we were trying to do was create capacity, not to reinvent the wheel. So we thought, well, if we could take that device and replicate it, that would be a good place to start. Of course, we couldn't get access to the devices because they're not commonly used in the NHS anymore, but they did have one in the Anaesthesia Museum at UCLH. So we went and took one out of the Anaesthesia Museum, and the engineers basically started by cutting it open and reading all of the internal measurements and what's called reverse engineering it so we could create an exact replica. And I think we also bought one off eBay from memory as well. So we copied and improved it. So the first thing that we did was form an exact replica of this previous device, and that's what I've shown here. But I'm sure, as many of you remember, there's a couple of things. First of all, CPAP devices are very oxygen hungry, and oxygen was a particularly constrained resource at the time, because obviously all of our hospitals were getting bombarded with patients that were using a lot of oxygen. So anything that we could do to minimise how much oxygen one of these devices used would be incredibly valuable. So the engineering teams did a lot of work, computational fluid mechanics analysis, engineering design work to minimise how much oxygen one of these devices used. And then we also did a lot of work on the breathing circuits, which are the valves and masks and pipes that basically connect the flow generator, the device, to a patient. And we managed to significantly reduce the oxygen utilisation and create a Mark II device. I'm going to talk to you through the timescales, but you're very welcome to pass that one round too. That's one of the Mark II devices. And we moved really quickly. So I think what was really key here, and I want to get across, was that the problem came from a clinician. So it was people on the ground who were treating patients and understood what that meant, who were the source of the innovation, and the engineers followed by creating the tools to respond to that need. But from a standing start, so that drink that we went for was on the 17th of March. By the Sunday, which was within 100 hours, the engineers with Mercedes had made the first prototype of the Mark I device and were back in UCLH testing it on the wards. Now, that never happens in peacetime. So within 100 hours, we were testing first prototypes in the hospital. We then did healthy volunteer testing and did patient evaluations, but within 10 days of that first meeting, we got regulatory approval from the MHRA for the Mark I device, which was the replica of the previously CE-marked whisper flow device. And then 2 days later, we got regulatory approval from the MHRA for the Mark II device, which was the device that minimised how much oxygen the devices used. We were kind of doing this outside of any mainstream kind of activity at the time, but through David Lomas managed to start talking to the powers that be and ultimately got a contract from the government to make 10,000 of these. The Mercedes factory were able to manufacture them at a rate of just over 1,000 a day. So from that first meeting, by the 15th of April, 10,000 devices had been manufactured and they were ready to go out to the NHS. And they did. They ended up going out to over 120 NHS hospitals. But just a quick nod to, of course, one of the things that you think of as an engineer is that nothing operates in isolation. So I think engineers are quite good at being system thinkers. And so when you're treating someone for respiratory failure with CPAP, you don't just need a flow generator. You need all of the tubing and the masks and the filters, etc. But you also need to be able to monitor the oxygen in that they're inhaling through oxygen analyzers. But of course, for the same reasons that we didn't have enough CPAPs and ventilators, we didn't have enough oxygen analyzers. Basically, we had to make those too. So we had to make 10,000 of those. So at the time, I think, did we say there were 400 oxygen sensors left in the country, and we bought the lot. And they were medical grade oxygen sensors to make our own analyzers, but we needed 10,000. And so Tim and colleagues had the brainwave that actually, if you look into the motorsports or automotive industries, they use lambda sensors to detect the concentration of oxygen in gas exhausts. And of course, there weren't supply chain restrictions on lambda sensors for the motorsports industry. So we ended up making this device, which I'll pass around as well, which was a new oxygen analyzer. So we got regulatory approval for that as well, and made 10,000 of those. That also went out boxed in the same thing, but it really showed the ingenuity of using expertise from other sectors and bringing it to bear in healthcare in a crisis. So that's my final prop to Sandra, and thanks, John. So did it make a difference? We made 10,000 of them. It was to bolster capacity within the system. We partnered with an automotive just-in-time logistics company called GTEM, who did next-day delivery to any trust in the UK, and they went out to over 120 hospitals. So that was a hopefully valuable contribution. And then, as I said at the beginning, for the same reason that we in the UK had restrictions on medical devices because of supply chain constraints, many other countries were facing similar problems. So we released all of our designs and manufacturing instructions for free through a zero-cost licensing approach, so that other countries could set up manufacturing hubs. So ultimately, around 25,000 devices were made in manufacturing hubs in other countries, in particular in low and middle income countries. And we also worked with the government around international donations because we didn't need all of the 10,000 devices that we made here. So in the end, over 3,000 of the devices were donated overseas, as well as subsequent countries were met with different waves of COVID. And here's some of the examples of the manufacturing team. So, in terms of partnership opportunities, we ended up working with engineers and clinicians all over the world that we would never have had access to or known about, and they were all formidable. They were incredible. And, that ranges from engineers in Peru who found out about it because they were Formula One fans, through to people who were affiliated to charities that we worked with. But it was an incredible experience, and one that I think we learned a huge amount from and was incredibly motivating. So what did we learn? We learned many things. First of all, innovation has to come from people on the ground who are treating patients. So I think there's a history and an ethos often that innovation's done to clinicians and to hospitals rather than with them. And it's the wrong way around. You end up fixing the wrong problem if you don't go straight to the clinicians and let them be the idea generators. So that's fundamental. Secondly, simple engineering is incredibly elegant. The best engineering happens when you don't even know about it. And there's so many simple engineering solutions out there that just pervade our lives that we don't even think about because they're so simple and elegant that they just work. And there's an example of a zip here, because that's one of them. But I think often, and I say this with an academic hat on as well, often we need a simple solution to a very specific problem, which is a different way of tackling innovation to the research-led innovation world, and we need both, and they're complementary. And then the other part that we learned a lot about from was alignment and standardization. So when you look at that pipeline, and the reason that we could go so quickly was because a lot of the normal friction in the system, whether that's regulatory and being able to do trials, et cetera, was stripped down and was simpler and more accessible. Safety and efficacy were never compromised, but there was streamlining. And again, if you look to other sectors, this kind of approach is more mainstream. So this is a very simple example, but if you think of the cars that we all drive that come from different manufacturers, they're all standardized in terms of what petrol goes into them. And we just don't think about that because that's just part of our lives. But if we took that kind of standardization, streamlining approach into healthcare, there's a huge amount that I think we could learn from. So that closes out the pandemic section of my talk. And I'm just going to close with a few final slides about the work that we're doing now. So I came out of the pandemic, and obviously this work carried on for a few years afterwards because of particularly all of the international work and subsequent waves. But I found it quite challenging that when coming out of the pandemic, I felt like we lost a lot of the learnings. What really worked in the pandemic was that we had huge alignment of values, and that kind of speaks back to what I was saying about Marsden at the beginning. But we knew what problems we wanted to fix and why, and everyone aligned around that. Rome is kind of still burning. Like, we still have massive problems that we need to fix, and yet we've lost that kind of ethos. We need to bring that back. And I found it very challenging that some of those learnings like that, like the streamlining, the friction-free, like the clinically led innovation, and we know so much around how to do this, and yet it feels like we're not quite fulfilling on that capacity at the moment. And so when I came out of this, I didn't want to go back to kind of my business as usual life, and I wanted to move more into health innovation and try and use the things that I'd learnt to carry this on further. And so I am now seconded to UCL Partners, which many of you may know, the health innovation company that has Royal Free as one of its founding and extremely valued partners. And I'm Chief Research Officer there, and what I'm trying to do is to take some of these learnings into what we're doing on our day-to-day. And there's a lot that's really challenging at the moment, and whenever you read the media and the press, we all know we all know that the NHS is under extreme pressure, but I'd say there's huge opportunity as well, and I think we're at a very exciting point in time, and actually this has been London Life Sciences Week, and I've got colleagues in the room who've been at it, and I think it's been an incredibly positive and energising week. London, for all the reasons that we've talked about, so it's an incredible ecosystem to work in terms of academic excellence, life sciences expertise, clinical expertise, interfacing with industry investors. And so thinking of London as a kind of global testbed for innovation in healthcare, we have the opportunity sat there, and I think that's phenomenally exciting. We have the opportunity to do it, and I know we've got leaders in the room who are very active on doing it. So at UCL Partners, we've done a lot of work to understand a lot of the barriers that are faced by innovators at the moment, and the things we've already talked about and are framed in the discussions that I've already put forward. But things like pilotitis, everyone trying the same thing multiple times at multiple trusts, lack of streamlining of things like access to data for research and innovation, commercial arrangements, and also procurement and adoption. So the scale question is really significant. The NHS is potentially an incredible market for innovation, but at the moment it's highly fragmented how new technologies are adopted, and that's not standardised. Unless we can fix that kind of scale problem, that inhibits our ability to be a kind of global market for those innovations. But yet we have the opportunity, we can do it. And basically what we're building now at UCL Partners, UCL Partners has a historical, it's HIN, so Health Innovation Network, so it has extensive expertise about how you go from proven innovations and scale them out into the system. And what now we're building, working in partnership with multiple trusts, including the Royal Free, and it's been a real privilege to work so closely with Royal Free colleagues around it, is how we make NHS innovators, clinicians on the ground and operational staff, the ideas factory. So we kind of unlock the people on the ground who are treating patients and trying to solve the NHS's problems as the kind of reservoir of innovation, but then work in partnership to put in place all of those learnings that we've been talking about to make it as easy as possible to go for those ideas to innovations that can be adopted and scaled into our system. And that involves working in partnership locally, and I'll mention slightly more about that in a moment, but also thinking about global partnerships to deliver on scale and market access, and also thinking very creatively around how the NHS creates value, and if we can create upside that can be reinvested back into the NHS. We really need that, because we're at a point where fundamentally the UK economy is not going to grow fast enough to meet the kind of increasing demands of the NHS, so we need to be creative around new ways to generate upside that can be reinvested into patient care. And of course, it's a real privilege to work with the Royal Free around this. But the work that we're doing, UCL Partners is a partnership across North Central London and North East London. And we're working across these 5 trusts in the first instance to deliver on this. And what's really exciting is that if we can work really closely in partnership across these trusts, and we have a patient base of over 5 million patients, which is bigger than some countries in the world. So we start delivering on that market and scale through our local partnership base. And this is ongoing work, we're just getting started. It's all being co-designed with clinicians here at the Royal Free as well as at the other hospitals. And it's also been a real privilege to work with Judy and the Royal Free charity teams to think creatively around the role of philanthropy and private investment in this kind of work. So I'm going to stop there. Thank you very much.